All right, so one last thing I wanted to mention about the periodic table before moving on is to be familiar with the labels for the groups. All right, there's different ways that these things go by. So one way is just to number them 1, 2, 3, 4, 5, 6, 7, 8, 9. But remember that there's also this practice of dividing things up into the A group elements or the B group elements. All right, the A group elements are the far left two, and also starting over here once you're at boron. All right, so notice that all those have A's after them. All right, and all the transition metals in the middle have B's after them. All right, they have Roman numerals. All right, sometimes they use a hybrid of this. Like for example, they might call this the number 4A. All right, but just translate that Roman numeral into 4A and you would be fine. So the next thing that we talked about when we after we talked about basic atomic structure was the location of the electrons. All right, and this is a subject that has evolved over time. It started off with an original idea of how the electrons were arranged in an atom. All right, so we knew that there was a nucleus, we knew that there was electrons outside of that nucleus, but we didn't exactly know how those electrons were arranged. The first idea was this Bohr model, all right, and that was the one that you would probably be familiar with, the way they described atoms back in science classes before high school, where you had the nucleus right here in the middle, and then we had these things called energy levels, which corresponded to distances away from the nucleus that an electron could be. All right, and remember we said that we could have 2 electrons in the first level, we could have 8 in the second level. All right, we could have another 8, and like back, a while back you learned that there could be 8 in that third level, and we would only have 8 valence electrons. But remember, when we go on to the electron cloud model, we learned that there could actually be more than 8 in that third level. It's just that you can't explain that using this particular model. All right. So the thing is, even though the Bohr model is technically incorrect in some ways, it still is often used. And I like to use the analogy in the same way that we use stick figures. All right. Stick figures don't look anything like a real human being, but they provide a value in being able to express very simple concepts about a human figure without having to go through the effort of making it completely accurate. All right. The Bohr model was later modified to the electron cloud model, all right, which also, I would say that outside of chemistry class, it's more commonly called the quantum mechanical model. And this is the one where instead of talking about these neat rings around the atom, we instead say that electrons exist in these regions of space called orbitals, all right? So instead of having that innermost circle here, that first level where there's 2 electrons, we would say that there is that in that first level, what you have is an orbital. It's an s orbital, and that 2 electrons could exist in that. All right. There's a lot of differences between this model and the Bohr model. One of those differences is that sublevels could exist. All right. So remember, in the Bohr model, we just said that 8 electrons could fit in that second level. All right. But as far as the way we're drawing this, all 8 of these electrons could be considered to be equal. All right. When we are talking about the quantum mechanical model, remember those 8 electrons are actually split into sublevels. All right, there is the 2s level. There's an s orbital in the second level, but then there are these 3 separate p orbitals. All right, so when you hear the term sublevel, it means like s versus p. All right, so how do you get 8? How do we reconcile the fact that we had claimed that there were 8 electrons that could fit in the second level here? Well, if you look at the second level in this, you've got 2 that could fit in the s orbital. You got 2 that could fit in this p orbital, 2 that could fit in this p orbital, and then 2 that could fit in this p orbital. All right, so there still are 8 electrons that could fit in that second level. It's just that the second level is split into sublevels. You've got the s sublevel, which is this 2s orbital, and then you've got the p sublevel, and the p sublevel actually consists of 3 separate p orbitals. All right. So remember what the orbitals represent. They represent a region of space where there is a 90% probability that you would find a particular electron. All right, so if you're an electron in the 2s level, that means you basically spend your time in randomly moving around in this region right here. All right, so remember, since it's 90% of the time, there could be times that the electron is a little bit outside of that. But that's what the definition of an orbital is. One other difference I want to point out about the Bohr model versus the electron cloud. In the Bohr model, we talked about things as being in energy levels, and you use that term energy levels. All right. In the quantum mechanical model, we don't generally say energy level, although the concept is still the same. Instead, what they use is what they call it either the principal quantum number, or they represent it with an n. All right. So the n value for the 1s orbital is 1. The n value for any of these orbitals right here is 2. Conceptually, it's the same as energy levels. So don't get thrown off if someone describes something as like the n. What is the n value for a particular orbital? So in talking about the Bohr model, remember that there's the classic experiment, which provided the reason for why it was proposed in the first place, and that was called the atomic emission spectrum. Basically, what happened in that experiment was when you took hydrogen gas and you excited it, it gave off light, and that light could be passed through a prism. And what we noticed is that instead of the light being all of the possible types of light, we only saw certain colored bands. All right. And one thing that we know about light is that the color of the light corresponds to the wavelength of the light, which is essentially the same thing as saying the frequency of the light. Right. And that corresponds to the energy of the light. All right. So what this indicated is that when you excited the hydrogen atom, only certain energies were being given off by the atom, not all of them. It's kind of like saying that when someone talks, they either speak in high, medium, or a low sound, but never anywhere in between. All right. And this information was used to basically drive a model. Someone tried to explain what does this mean about the structure of the atom, and what was the explanation is that when the electrons in the atom were excited or absorbed some energy, they could get boosted up to higher levels. All right, so that's basically what zapping the hydrogen atoms with some electricity would do, is that they would boost electrons that would normally be in this lower level up to a higher level. But those higher level electrons are in a higher energy state than what they want to be. And so when things are in high energy states, they generally want to get back to lower energy states. And when they went back to their lower energy levels, they gave off little bits of light. All right, and the amount of light, the type of light that they gave off, corresponded to the amounts of energy given off from a particular transition. All right, so if you went from the third level back to the second level, that would give off a certain color of light, all right, corresponding to a certain frequency, which corresponded to a certain energy. All right, if you went from the second level back to the first level, that would give off a different color. All right, and remember, I'm using the term color, but what that could actually mean is a type of invisible light. For example, a radio wave, all right, is a type of light, a type of electromagnetic radiation with a particular frequency, even though it's not really a color, all right, but we're just calling it a color just to differentiate between types of electromagnetic radiation that have different frequencies, all right. Are some of these different colors? Yes, the ones that correspond to wavelengths that are in the visible range that that our eyes can detect. Yes, those would be different colors. But remember, one of these could be like a real actual color like purple, whereas another thing could be something like a radio wave. All right. And hopefully you can kind of visualize this. If something went from the third level back to the first level, that would be more energy than if you went just from the third level to the second level. You can kind of think about it like jumping from the third step of a ladder down to the first step would give off more energy than just going from the third step to the second step. All right, and that would correspond to a type of energy that was more towards the higher energy, which is the purple end, all right, than the red end. All right, remember, one way you can always remember that is that the more dangerous type of light is the ultraviolet. All right, so think of that. The violet end is the higher energy, but the over here infrared. All right, that's the that type of energy is not really that harmful. So make sure that you can interpret the diagrams corresponding to this that are in the reference guide. So, for example, if someone were to say, if an electron were to jump from the 6th energy level, all right, notice they use ends here instead of energy levels, to the 3rd one, what would the wavelength be given off? All right, so you could have to find, okay, this ring right here is the 6th ring, this is the 3rd ring right here, and we could say that that would give off 1094, and that would be in nanometers. All right, so make sure that you can interpret this type of a guide right here. So getting back to the electron cloud model, remember that when you have an actual atom, that you have electrons that are in the orbitals. All right, and there's a couple ways that we can indicate how those electrons are in those orbitals. One was called an orbital notation, which is like this, where the direction of the arrow indicated the spin, all right, but the level here indicated like this image right here shows how they would be in the different orbitals. All right, so this would represent the s orbital in the first level. This is the s orbital in the second level. Each of these circles here would represent one of the p orbitals in that 2p level. All right. Remember, the direction of the arrow indicates the spin, and there were these rules that dictated how the electrons could fit in these. All right. The rules are summarized in one second. Are summarized right here. Basically, electrons want to be in the lowest energy orbital available. In order to be in the same orbital, they have to spin in opposite directions. All right. Remember, we call it paired if they're in opposite directions, and if they're at equal energy orbitals, they want to maximize the number of unpaired electrons. And we went through examples where what that means is that if you had 7 electrons, first one would be up, down, and then here, since these are equal energy, it would be up, 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 all right, or it could have been down, 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 all right, as long as when you're filling those, they all go in the same direction. I want to point out that there is actually, these are sometimes drawn in a little bit of a different way, where they're drawn horizontally, like where this would be the 1s, this would be the 2s, and these would be your 2p orbitals here. So you just go up, down, and then you do up, up, up. All right.